Okay, so so in this lecture, we start with discussing what is called separating sets. So suppose you have a graph G. Let's say a graph is given, as in the picture. Let's say, and you have sets, let's say x and y of this the vertex set. Right? So x and y are some subsets of the vertex set, and then now let us look at the paths that go from x to y. You have you have any vertex of x you can take, and then you can see like, okay, take any path that you want. It starts from a vertex of x and goes to some vertex of y, right? Any paths, right? So all possible paths you can see. So each of these are basically paths starting from this vertex, right? Here, and similarly, you have other paths, and now if you look at these paths, you will see that every such path must go through at least one of these vertices, right? Or this edge. Right? So every path must use either either of these two vertices, or this, or maybe both, right? But at least one of these must be used. Right? So without using one of these vertices, you can never go from a vertex of x to a vertex of y. So once you see that, what you can recognize is that if you remove these two vertices and this edge, then essentially there is no path going from x to y. Right? Every path uses one of these, so therefore if you remove them, there is no path from x to y. So such a subset of vertices and edges, whose removal makes sure that there is no x to y path, is called an xy separating cut. And here is a formal definition. So you have x and y are subsets of the vertex set V, and you have a set which is a subset of the union of the vertices and edges. And if S is such that every path in the graph, right, contains a vertex or some edge from the set S, then we say that S separates x and y. So here are some more examples. So you have this graph with x is these two vertices and y is these three vertices, and then you will see that every path from x to y must pass through either the vertex v1 or v2. Right? So therefore v1 comma v2 is a separating set, right? Even without any extra edges, v1 v2 by itself is a separating set. For example, you can also see that if we don't, so there is this edge E, and then there is a vertex U. Okay. So if you don't use the edge E, then you must use the vertex U to go through this, right? So therefore, E and U together forms another separating set. And similarly, the edges E dash and E double dash, one of these must be used to go from x to y, right? Always, every path must use one of these. So therefore, those three, right, form a separating set. And similarly, E1 and E2, right? These three edges, one of these must be used by every path. So therefore, xy path. Therefore, that is also a part of an xy separating set. So each of these is basically an xy separating set. Now, if if just if the set S contains only vertices, then the separating set is called a vertex cut. and if S contains only edges, then it is called an edge cut. So we have already some examples of that here, right? S2 is a vertex cut because V1, V2 is just vertices. S3 and S4 are edge cuts because they consist only of edges. S1 is neither a vertex cut or a nor an edge cut. Right? Here is another example, right? So you have this graph, and let's say that you have this is your x and this is your y, right? Then you see that every again xy path must use one of these edges e1, e2, or e3. So therefore, they form an edge cut. Similarly, it must use either u or v. So therefore, u comma v is a cut. Similarly, one can see that v1, v2, right? This one, v1 and v2, right, forms another vertex cut. So you have these edge cuts and vertex cuts, and similarly, E3, right? No, this is not an XY cut, but this is okay. So this is just a cut, but it's not an XY. So we are looking for an XY cut. So yeah, so U and right, E6, E5, and E4, right? This forms. 1 second, sorry. Don't need E6 here, right? Yeah, E6 is required because I have a path from that. Yeah. So yeah, so V1 and E6, E5 and E4 forms another cut separating set, but it is not an edge cut, right? But if you want an edge cut, then E1, E2, E3, or E1, E2, and then E6, E5, E4, right? This set is also an edge cut. So we have several possible edge cuts, and then we can talk about the cuts which is also the smallest size, etc. Because that comes as some important parameters. So we are going to define that. So if a subset of the vertex set is separating, then as we mentioned before, it's called a vertex cut. And if the subset is separating, which is a subset of the edge set is separating, then it's called an edge cut. If you remember, we have already defined what is a cut vertex and a cut edge, right? So a cut vertex is basically a vertex cut of cardinality 1, and a cut edge is basically an edge cut of size 1. So if you have such graphs, right? For example, so in this separated, so therefore this edge is is an edge cut by itself, so it's a cut edge, and you will remember this. And these vertices are also cut vertices because just removing one of them, we have a graph becoming disconnected, right? Okay. Now a graph is called separable if it has a cut vertex. So any graph with a cut vertex is called separable, right? And non-separable graph is one without a cut vertex. Okay. Now here is another definition, right? So two paths are said to be internally disjoint if they have no internal vertices in common. So what I mean by internal vertices is the vertices apart from the endpoints, right, which can be same, but the endpoints of the paths can be common, but other vertices cannot be common to the paths. So two paths which are internally disjoint, then necessarily form a cycle, right? So if and if they have common endpoint, they form a cycle. If they don't have, then of course it's not. So paths can be like, so for example, this path and this path are internally disjoint. They don't form a cycle. But if this path and this path is also internally disjoint, so if the endpoints of both paths coincide, right? If there are two UV paths which are internally disjoint, then they form a cycle in the graph. Okay. Now, suppose you have a set of UV paths that are internally disjoint. How do you define this? A set to be internally disjoint, right? If any two of them are internally disjoint, then we say the set is set of UV paths are internally disjoint. So here are some examples. So you have the vertex U and the vertex P, and let us look at the paths. So the blue paths, right? The blue path here has no vertex in common with the white path, right? So the white path and the blue paths have no vertices in common except U and V. Therefore, these two paths are internally disjoint. But if you take the some other path, right? For example, let's say that I go from U to this vertex and take this, right? Let's say that I have this. Now this path is not internally disjoint with the blue path or the white path, but you can probably find another path. Let's say this one, right? Which is internally disjoint. So such paths are called internally disjoint, and yeah, so you get the idea. So we will use this notion to define some other parameters later, not at the moment. Now, so here is a theorem that will be very useful for us. The connected graph of of at least three vertices contains and which does not contain which does not contain any cut vertex, right? Can be characterized as the set of all graphs where any two distinct vertices there is an internally there are two internally disjoint paths between them. So the theorem says that a graph on at least three vertices, connected graph on at least three vertices contains no cut vertex if and only if for any two distinct vertices U and V, there are at least two internally disjoint UV paths. So this is basically the result. So how do we prove this? Okay. So to prove this, what we are going to do is the following. So first we prove one direction where we assume that if there are two internally disjoint UV paths between any two vertices, then the graph has no cut vertex. Right? This is the easy part. So how do we prove this? So let us say that you have two vertices. Between any two vertices, right? Any two vertices, there are two internally disjoint UV paths. Right? So if this is true for any pair of vertices, right, and you pick some vertex, let us say a vertex, let us say x, And now the question is that can x be a cut vertex or not, right? So take some arbitrary vertex x. Now if x is a cut vertex, what does it mean? It means that x basically separates the graph into at least two components, right? So you started with a connected graph. So if x is a cut vertex, x must separate the graph into at least two components. Now we know that if it is going to be two components, then there will be some vertex in one of the components and another vertex in the other component. So let us say that pick two vertices, let us say u and v, right? Now between these two vertices u and v, we know that there are two internally disjoint paths, right? So if I pick any two vertices, right, as x and y, I mean not x and y, u and v, okay, then you know that there are two internally disjoint paths between u and v in the graph, right? Which means that uh, you know maybe one of the paths is using the vertex x, but then the other paths cannot use the vertex x because the paths are internally disjoint, right? And x is not one of the n vertices, so therefore there is a path from u to v after removing the vertex x also. So for any vertex x in the graph, this is true, right? Because for any pair of vertices, the assumption is that for any pair of vertices, we have two internally disjoint uv paths. So where were we? Yeah. So between u and v, there are two internally disjoint paths. Mean that no, at least one path exists in G minus x for any vertex x between any pair of any of the remaining vertices. So which means that G minus x is connected for every vertex x, and therefore the graph must be connected. G minus x is connected. So one direction is over, right? Now what about the other direction? So other direction, so the other direction, we want to show that we have a connected graph of order at least 3 and it contains no cut vertices, right? And we want to show that there are two internally disjoint UV paths. So how do we do this? Okay. So one thing that we can start with the assumption is that you have these vertices u and v in the graph. You are adjacent, right? So you are saying that for any two distinct vertices, there are two internally disjoint UV paths in the graph, right? Now let us assume that u and v are adjacent. That is the first case, right? So if u and v are adjacent, then what can we say? Okay. Now if u and v are adjacent, I say that this this edge uv belongs to some cycle of the graph, right? Because the edge uv cannot be a cut edge in the graph that we are considering. And why is that? Okay. So yeah. So if we take a graph of our assumption that a connected graph, so we have a connected graph of order at least 3 and no cut vertices, then we say that the edge, you pick it up, right? UV be any two vertices and you pick up the edge UV, right? This edge cannot be a cut edge. And if an edge is not a cut edge, then we have already proved earlier that it belongs to some cycle of the graph, right? And therefore, the UV edge belongs to some cycle, and if UV edge belongs to some cycle, the vertex U and V must be part of that cycle, right? So therefore, U and V are in the cycle, and if there is a cycle, then of course there are two internally disjoint paths between U and V, because UV edge is one path, and then the other part of the cycle minus this edge is the other path, right? So these two internally disjoint paths we have. Okay, so if u and v are adjacent, fine. Now what if they are not adjacent? Okay. If they are not adjacent, okay, maybe I will I will present the first part formally and then draw some figure to. So the first part of the proof is again here, right? We have a connected graph, and any two vertices are connected by two internally disjoint paths is given, right? So in G minus B, where B is any vertex, there will be a path between the vertices that we are considering, right? So therefore, the graph is connected, and G minus B is connected, and therefore V is not a cut vertex. So since V was arbitrary, right? We pick it up any vertex V, we know that no vertex is a cut vertex. That is the proof of the first part. So to prove the second part, I use the help of this figure, which is easier to explain, right? So if U and V were adjacent, we said that we have a cycle, right? That is our claim. Now suppose U and V are not adjacent, right? So what we are going to do is we are going to use induction on the the distance between U and V, right? And the base case is when U is equal to 1, and then we have already done that, right? That's an edge between U and V. And then therefore we can assume that say that for any k less than any value less than some fixed k, right? If the distance is less than some fixed k, then of course the result is true, right? So now we are going to now this picture will really help you understand this. I hope, right? So you have a UV path of shortest length, right? So you pick this yellow path which says that we have this UV path of shortest length, right? Now we assume that the length of this path is k, right? And for anything less than k, we know that we have our result, right? So if the distance is less than k between U and V, then you know that there are two internally disjoint UV paths, right? So now we take this distance be exactly k, right? So UV has distance k. Now if the distance is exactly k, there is the shortest path must have some sequence of vertices, let's say v1 v2 etc., right? And the last vertex before k is say v dash, right? So v dash is the vertex which is v dash is the vertex which is just immediately preceding the vertex v. Now because the distance from v to u to v is k, the distance from u to v dash cannot be less than, it will be equal to k minus 1, right? Because it cannot be larger because we already have a path. So therefore the distance is at most k minus 1, right? So the distance between u and v dash is k minus 1. And because of our induction hypothesis, now we can say that there are two internally disjoint paths from u to v dash, right? So let us say that p dash and q dash are these two paths. So there is a path p dash from u to v dash, and then a path from u to v dash, which are two internally disjoint paths. Of course, these paths need not be using the edges of the shortest path that we considered before, or maybe they are using. We don't know, right? Doesn't matter, but they are internally disjoint. That's all we know. Now, so what we know is that like there are these two paths, right? P dash and Q dash. Now, if you look at so there is no cut vertex in the graph, right? That is our assumption. Therefore, if you pick up the vertex v dash and remove it, there is still a path in the graph from u to v, right? Because v dash cannot be a cut vertex, right? So there is some path from u to v in the remaining graph. Now, what is this path, right? So this path, let's call it r dash, right? The white edges. So this path r dash, does not use the vertex v dash that we know, right? Of course, it could be intersecting, p dash, q dash, or some other vertices, or maybe entirely, disjoint, except the starting vertex must be the same, right? Because each of these paths uses the vertex u, right? So if I look at the path r dash and then pick up the vertex, that is visited by either p dash or q dash, right? Which is in common with either p dash or q dash. Look at the last vertex along the path from u to v, right? I mean, some vertex must be there. I mean, it could be equal to u, but some vertex must be there. So, with purpose of generality, we can assume that that vertex belongs to p dash, right? It could be either p dash or q dash. Doesn't matter, right? Now, so let me call this vertex as x. Okay, so this vertex I call as x. Now, what we just need to observe is that if you look at the path that we define as follows, that you then you take the path p dash to go to x, right? And then take the remaining part of r dash and going to the vertex v. This path cannot be cannot have any vertex in common with q dash, because p dash and q dash were disjoint. And then I take the path u to v dash using q dash, and then take the edge v dash k. This path is another path which is also internally disjoint, because again v dash is not part of g minus v dash, right? So therefore the path r dash cannot have v dash in common, and then we have not taken anything else. So therefore this path u q dash v dash v is also another path. So these two internally disjoint paths exist between u and v. So therefore we have the induction, and that is how the result follows. This is the formal argument. So we have the graph G, right, with at least 3 vertices and no cut vertex, and you pick up 2 vertices, let's say u and v, right? Now, if the distance is 1, as we said before, right, and since there is no cut edge, right, we immediately get the result that u and v are part of some cycle. Now, if not, then we assume that the result holds for any pair of vertices where the distance is strictly less than k, for k is at least 2. And then if the distance is k for u and v, then we take the shortest path of the path of length k between u and v, and call this path, let's say, p, right? Now what we do, we pick up v dash as the predecessor of the vertex v along this path p, right? And then we know that the distance between u and v dash is actually k minus 1. So as we mentioned before, there are two internally disjoint paths, v dash and q dash, from u to v dash by induction hypothesis. And because there is no cut vertex, right, g minus v dash has a uv path in R. Then if x is the last vertex, right, of p dash union q dash, which intersect with r dash, right, then we can assume that it belongs to one of these paths, let's say p dash, and then the path from u to x using p dash, and then taking the remaining part of the path using r dash, and similarly going from u to v dash using q dash and taking the edge v dash p are two internally disjoint uv paths. So now we define blocks. So what are blocks? Blocks are basically maximal non-separable subgraphs of a graph. So we have a graph G. We defined a graph to be non-separable if there are no cut vertices, right? So look at the maximal subgraphs without cut vertices. They are called the blocks of the graph. So here is a graph, and I have marked the blocks. So this is a block by the edge by itself, because I cannot include anything more, right, to this subgraph, because this vertex is a cut vertex, right, in that graph. So this subgraph is fine. Then B2, right, this fourth cycle is another subgraph, and then you have this white subgraph. Then B4 is the edge, B5 is the triangle, and B6 is another triangle. Then B4 is this K4, right? Complete graph on 4 vertices, and B8 is the cycle. So each of these blocks, these subgraphs are blocks, and they are maximal subgraphs without cut vertices, right? So they are basically non-separable subgraphs, and these are the blocks of the graph. So we will need it a little later, but not at the moment. So here are some questions for you. So first, the proposition that so given a graph G, right? So show that any two blocks of G have at most one vertex in common. So this is one question. Then the second is that the blocks form a decomposition to non-separable subgraphs. It's kind of immediate to see, but formally write it. Second question is to prove that a connected graph is non-separable if and only if any two edges of the graph lie on a common cycle. Okay. So we earlier proved that any two vertices, right, for a graph without a cut vertex except for the edge, single edge, any two vertices lie on a cycle. Now show that a connected graph which is non-separable, then there are any two edges also lie on a common cycle. Okay. Now we want to define connectivity. So the idea of connectivity, so we started with the notion of graph being connected. So a graph is connected if I can go from any vertex to any other vertex by a walk, right, or a path. Now, so the first graph that we have here, which is a tree, right, as you already know, is connected, and we have the graph to be connected. But if you look at this, you see that if you remove any edge of the graph, it becomes disconnected, right? Or any like any of these internal vertices, right, will keep the graph disconnected. So therefore, it is connected, but it is still, you can see that it's kind of weak, right? On the other hand, if you look at the second graph, right, by removing one edge, you cannot disconnect the graph. But of course, there is a vertex whose removal disconnects the graph. Then the third graph, if you remove any edge or even any vertex, one vertex, you cannot disconnect the graph, right? So for that graph, you can see that it is more, in some sense, it is more connected than the first graph, right? And if you can find a pair of two edges whose removal disconnects the graph, right? For example, this and this. And what about vertices? Can you remove two vertices to disconnect the graph? Yes, you can. Right? If you remove this vertex and this vertex, again the graph gets disconnected. And on the other hand, the third graph, you cannot remove two vertices to disconnect the graph or two edges to disconnect the graph. So, the fourth graph, right? This one. But even that graph is not as connected as the final graph, which is a complete graph on 5 vertices. All these graphs are on 5 vertices, right? The last graph, where any vertex is connected to any other vertex by a direct edge, and therefore without removing at least 4 edges, you cannot disconnect. So connectivity notion, becomes more and more strengthened, right? So we can now try to define this as a form a parameter and say that okay, we define connectivity, right, in some way, right? Related somehow we want to capture this kind of a notion. Right? So a graph is said to be k connected, right, if every vertex cut has at least k vertices. So we already defined what's a vertex cut, and if every vertex cut, the smallest vertex cut, for example, has k vertices, at least k vertices, then the graph is k connected. right? And the connectivity is basically the minimum size of a vertex cut in the graph, and or the maximum number of the maximum k such that the graph is k connected. Okay? So that is called the connectivity, and is denoted by the Greek letter kappa of G. Right? So the connectivity is the minimum size of a vertex cut. So in the first graph, it is disconnected. So the connectivity is 0 because it is not even connected. So you don't have to remove anything to make it disconnected, right? The second graph, the connectivity is 1. If I remove the vertex in the middle, the graph gets disconnected, but the graph is otherwise connected. Okay? And the third graph, which is a cycle, the connectivity is 2 because by removing one vertex, I cannot disconnect the graph. The fourth graph, right, connectivity is again 2 because I have a pair of vertices whose removal disconnects the graph, right? These two. And for the next graph, the connectivity is actually 3, right? You can show that by removing 2 vertices, I cannot disconnect the graph for any pair of vertices. And what about the connectivity of the last one, right? I mean, this is interesting because the graph is complete, by removing a vertex, right, any subset of vertices, I cannot disconnect the graph at all. So what do we say about the connectivity of the complete graph? Now, to take care of this situation where we cannot really say anything like this, we define the connectivity of the complete graph to be the number of vertices minus 1. So we redefine the notion of connectivity to be the minimum set of vertices whose removal either disconnects the graph or results in in the trivial graph, right? The single vertex. So this way we can formalize this. And yeah, so here is the statement, right? So connectivity of the complete graph Kn is basically defined to be n minus 1, so that we can redefine the connectivity as the smallest number of vertices whose removal results in either a disconnected graph or the trivial graph. So here is a question for you. So suppose you are given the cube graph. I think we defined this sometime back. The cube graph was basically defined as a graph with the vertex set as the set of all binary strings of length n, right, or k, or qk if you are defining of length k, and then two vertices are adjacent if the corresponding strings have exactly one position different, right? I mean one zeros and ones. Yeah, so the Hamming distance is 1. And this graph, you will be able to see that, like, this graph is basically, for 3, it will be the cube graph, right? Which represents the skeleton of a cube. And then for higher dimensions, it will be called hypercubes. So 4-dimensional cube will be like another cube, and then the corresponding vertices will be made adjacent. So this is a nice structure for this. Now, can you find out the connectivity of QK? Maybe a little difficult, but it will be interesting. Then another question I can think of is like, what is the connectivity of KMN? Complete graph, complete bipartite graph on a vertices and n vertices. Now, so given a graph, so we saw that we can talk about whether the graph is connected. Then we can talk about how well it is connected in terms of the connectivity, at the minimum number of vertices that will disconnect the graph. Now, so therefore we have this parameter connectivity, and it says that if the graph is connected, then between any not between any if you so for any subsets of vertices, let's say u and v, right? subsets of vertices A and B of the vertex set V, then you will be able to see that, like, if you want to separate them, you need to delete at least k vertices, right? Now, now we can ask, okay, the graph is k connected, right? But I mean, is it slightly better connected than this or not, right? I mean, you can ask, like, can you actually remove some edges and still keep the k connectivity? And you can try to do it, right? So you take the graph and see if I remove this edge, whether the remaining graph is k connected, and you can keep on doing this. And once you do this several times, you will end up in a stage where if you remove any of the edges, then the graph is no more k connected. So you stop just before the removing that edge, and then such graphs, I know that if I remove any edge, it is not k connected, but the graph is k connected. So that is called critically k connected graph or minimally k connected. So a graph is minimally k connected if it is k connected, and for every edge in the graph, g minus e is not k connected. So this actually allows to study, some structural properties that one can try to see, like what basically defines the connectivity and things like that. But it is not very well studied yet. I mean, there have been several attempts, but not much is known about the structure of such graph. Of course, there are some properties known. We may not discuss all of them. In fact, we will not discuss many of them, except maybe for the case k is equal to true. So here are some examples of graphs with minimal connectivity, right? So here is a graph which is minimally one connected. You know that they are basically the trees. In fact, we asked it as a homework question to show that trees are essentially minimally k connected, right? That graph is connected with minimal number of edges. That is precisely the trees. Right? So graph is minimally one connected. It is a tree. And here is an example of a minimally two connected graph, which you will see, which is a cycle, right? Cycles are two connected. And if you remove any edge, there is a cut vertex. But they are not the only two connected graphs, right? For example, here is another one, which is the graph on the left side below, right? That is another minimally two connected graph. You can verify that if you remove any edge of this graph, you will still get a connected graph, but it is having a cut vertex. So removal of every edge leaves a cut vertex. So it would be a very nice exercise to think about minimally two connected graphs, right? What defines a graph to be minimally two connected? Right? So you take a two connected graph and see that when can you say that it is minimally two connected? So think about this. That is an excellent exercise. In fact, I would recommend it. Then here is a minimally three connected graph, right? If you remove any edge, the graph is not doesn't have a cut vertex, but you will see that it is two connected. That you can find a separating set of size two. So you take this and see how you can find the. So for every edge, you pick the edge and see, like, can you actually find a separating set of size two after removing that, and verify that this one is actually three connected, that there is no two separating set in this. So that will be a nice exercise again. More questions? So first of all, for this graph below, right, there are the 5 graphs below which I have given. Check first of all if it is two connected, then verify whether it is minimally two connected. And third one is to find out the connectivity, exact connectivity, right? And then fourth one is to find the minimum degree. Okay? Right. So this is something very easy to do. Now, if you look at these examples, you will be able to see some relation between the connectivity degree, etc. That we will look at in the later part of this class. Okay, then second question is to show that if a graph graph G is two connected, then for any two vertices of this graph lie on some cycle of the right. If the graph is two connected, then any two vertices lie on some cycle of the graph. Then third question is to prove or disprove the following statement. So if G is a graph which contains a cut edge, let's say E, then show that the graph G contains a cut vertex. Just 1 second. Okay, so that if a graph is having a cut edge, then it also has a cut vertex. So this is a statement, and see whether it is true or not, and then try to prove or disprove it. Okay. So the fourth question is that given a k-connected graph G, and suppose you take the graph and add a new vertex, right, and make it adjacent to any k vertices of this graph. So take a k-connected graph, add a new vertex, right, make it adjacent to any of the k vertices. Then show that the new graph that you obtain, let's say it's called G dash, that graph is also k connected. Right? So if you take any k connected graph, pick any k vertices, add a new vertex adjacent to each of these k vertices, then the graph that you get is also going to be k connected. Now to give another exercise, I want to define something very simple, that it's called subdivision of an edge. So subdivision of an edge is basically like, you take an edge, then introduce a vertex in the middle, right? You just basically split the graph, split the edge, right, into two by introducing a new vertex. So this is basically deleting the edge UV and adding a path UWV where W is a new vertex, right? So this is what happens. We have the edge UV here, and this edge becomes the path UWV where W was not part of a vertex set in the graph. It is added now, right? It's a new vertex which is added, and then you have a UWV path. Now, if you add this to an edge, right, what happens to the connectivity of the graph? Right? So this homework that says that if graph is two connected, right, and then if you take the graph G dash obtained by subdividing an edge, right, then the new graph is also two connected. This is the statement. Now you can either prove or disprove it. So take a graph, pick any edge, subdivide it, and then you get a new graph, and see whether this graph retains the two connectivity of the original graph. Okay, now so since we are looking at lattice connectivity so far, now let us also see what we can say about the connectivity in terms of the edges. Right? Lattice connectivity is essentially, the idea is that like you have a graph, how well it is connected, in the sense that by deleting vertices, can you disconnect the graph, and what is the minimum number of vertices that you need to delete. Then you can also disconnect the graph by removing the edges, right? So if you remove all the edges incident with one vertex, that vertex becomes isolated, right? So therefore, the graph will become disconnected. So that is clear. And so now we can talk about the connectivity in terms of the edges. So again, here, first graph is of course not connected. So connectivity is not there. Then the second one is a tree. You know that the tree is connected, and then we also know that every edge of a tree is a cut edge, right? That is also something that we proved, right? A graph, connected graph is a tree if and only if every edge is a cut edge. So here every edge is a cut edge, which means that removing a single edge will disconnect the tree for any edge, right? And the third graph, again, there is some edge whose removal disconnects the graph. It's called a bridge or a cut edge, right? And this edge, for example, is a cut edge. So that is also not as well connected, right? Then you have the cycle, right? So cycles are two connected. If you remove any single edge, of course, it cannot disconnect the graph. So therefore, you see that you need to remove at least two edges to disconnect the cycles. So the cycles are two edge connected. Then you have this graph that we saw before, right? And again, you will see that you need to remove at least three edges to disconnect this graph. But again, that is also not as well connected as the complete graph, right? Where you have to remove at least four edges to disconnect in this. Right? So all these graphs are five vertices, but you can see that in some sense the notion of the well connectedness keeps on changing. Now, formally, for the graph has at least L edges. So what is the edge cut? The set of edges which disconnects the graph, right? Now, so the L graph is L edge connected. You have to remove at least L edges to disconnect the graph. And the edge connectivity is the minimum number of edges whose removal results in either a disconnected graph or the trivial graph. So this is the definition of edge connectivity. And in fact, the last part is required only if you are not looking at graphs which are not related. But anyway, that doesn't matter to us. Okay, here are some more examples. So we have the cycle graph where you know that the vertex connectivity we saw that it's actually equal to 2, right? Edge connectivity also we saw that it's actually 2. And you can see that there is another parameter we are looking at now, which is called the minimum degree, small delta, which is also 2. Right? Why we are looking at it, you will see when we look at the next problem. So the next question, next graph, you have vertex connectivity is actually equal to 1, right? Edge connectivity is 2 because you will see that every edge is part of some cycle, so you need to remove at least 2 of them to make the graph disconnected, and the minimum degree is actually 2. Then you have the third graph, which is K4, and for this, all the parameters are equal to 3, right? The vertex connectivity is 3, right? Edge connectivity is 3, and the minimum degree is also. Then the next graph, where the vertex connectivity and edge connectivity are both 1, and the minimum degree is 3. So if you look at all these things, you will see that there is some kind of pattern, or some relation between these parameters. Here again, vertex connectivity is 2, edge connectivity is 3, and minimum degree is 4. So you can see from this example, for that the vertex connectivity can be less than or equal to the edge connectivity, and it can be also strictly less than the minimum degree, right? They can all be equal. That we saw from the previous example. Now, if you look at more and more examples, you will see that this relation always holds. That the vertex connectivity is upper bounded by the edge connectivity, which is also upper bounded by the minimum degree. So this is the theorem of Whitney, 1932 or something, I think, that the vertex connectivity is less than or equal to minimum. The edge connectivity less than or equal to the minimum degree. Now, how do you prove this? Okay. So first we look at the cases which are trivial or exceptional cases. Like for example, when the graph is having connectivity 0, right? The edge connectivity and vertex connectivity are both equal to 0, right? Because it is not connected, you don't have to remove any vertex or edge to disconnect it, so it's both 0. And of course, it is at most the minimum degree because it cannot be less than 0. Then if the graph is complete, then we know that by definition, the vertex connectivity equal to the edge connectivity equal to n minus 1, which is also minimum degree. And why the edge degree, edge connectivity is n minus 1? Because if the graph on n vertices is complete, then you know that if you remove all the edges incident with one vertex, it becomes disconnected, right? And that is equal to n minus 1. So, and you have to actually prove that for complete graph, the edge connectivity is equal to n minus 1, which I have not done here, but it would be a nice exercise. Okay, so take it as an exercise and prove that if the graph is complete, then its connectivity is actually equal to n minus 1. There is no smaller cut. Now, without loss of nullity, we can assume therefore the graph is connected and not complete. Now, the second inequality is immediate, right? That lambda of g is less than or equal to delta of g. And why is this? I think I already mentioned this, so you can think about the details. And I think I already mentioned it here, right? Yeah. Okay. So now what we need to prove is that, what happens if yeah. So what else? The kappa and lambda, that the vertex connectivity and edge connectivity. So in order to do that, what we do is that so we are going to look at the edge cuts of a graph. Right? So what are the edge cuts of the graph? That you take any vertex set, right? Let's say S, look at its complement, and the edges between them is an edge cut. In fact, every edge cut is of this form, right? So you look at all the edges which separates. Of course, there is one side and then there is another side, right? You can put whatever is remaining on the other side. So every edge cut is of this form, that you have a set of vertices on one side and its complement on the other side. So if there are k vertices on one side, let's say S, then n minus k vertices on the other side, S bar. So all the edges between them. Now take any edge cut and then see whether these edges, how many edges are there in between. One possibility is that all possible edges are there, right? That there is a complete bipartite graph sitting between S and S complement. So if this is complete, that all possible edges are there, then what can say, right? So if all edges are in between, then you know that the total number of edges is k into n minus, right? That is the total number of edges. But now if you look at k minus 1 into n minus k minus 1, this is greater than or equal to 0. And why is that? Well, you can think about it, right? K minus 1 to n minus k minus 1 is greater than or equal to 0. And from this, you will see that k into n minus k is equal to n minus 1. And so we started with a graph, right? Which is not complete, right? Because for complete graphs, we said that this is actually equal to n minus 1, and I asked you to prove that, in fact. And if the graph is not complete, then we are saying that we have k into n minus 1 is greater than or equal to n minus 1. Now we said that this is a minimum edge cut, right? We picked up some edge cut of this form, and then suppose it is a minimum edge cut, then we get a contradiction, right? We are going to say that now, okay, n minus 2 is greater than or equal to k into n minus k greater than or equal to n minus 1. And this, therefore, we get a problem, right? So the edge cut cannot be a complete bipartite subgraph. So again, I have not completely explained this. I want you to think about this. That is the only reason. Okay. So if S bar is a minimum edge cut, right, then each vertex is adjacent to each other vertex of S bar, right? In that case, we know the number of edges in the cut is T into M or K into N minus K. And then, K minus 1 into N minus K minus 1 is greater than or equal to 0. It says that N minus 2, which is greater than or equal to lambda, greater than or equal to N minus 1. So, and this is a contradiction, and therefore, we can look at the remaining case that this cut between S and S bar misses at least one edge, right? So what I mean that is that some vertex, let's say x in S and some vertex y in S bar, there is no edge between x and y, right? For the minimum cut that we have. Okay. So therefore, you can find some pair of vertices x and y, right, in S and S bar such that there is no edge xy in this cut. Okay, so here is the picture representing that. You have this vertex x and the vertex y, and the edge xy is not. Now we make a vertex cut out of this edge cut. So you take this edge cut, look at the vertex x, look at all its neighbors in S bar. Right? Okay, all the neighbors of x in S bar. I get all of them. I put it into a set T. Then I will look at all the vertices in S that has at least some edge going to S bar. Right? I mean, there could be vertices here. There are a lot of edges here. Right? There could be many edges here. But without worrying about that, we are saying all the vertices in S which has at least some neighbor to S bar, right? So pick up all the vertices and then that goes into T. Okay. So pick up all the vertices which are neighbors of X in S bar and those vertices in S which has, right, which has some neighbor in other than X, which has some neighbor in S bar, right? So I will not include X, of course. And now, what happens if I remove T, right? T is set of vertices. T is the set of vertices, but every edge in this cut is now incident to some vertex of T. Right? And therefore, if I remove T, the graph x and y becomes disconnected, right? There is no path from x to y. And what is the cardinality of T? Cardinality of T is at most the number of edges, because every vertex that I pick has some edge incident to it, right? So that is the only reason we picked up that, and therefore it is less than or equal to the number of edges of the cut. So which means that it is less than or equal to the, and because we started with the minimum cut, it is less than or equal to lambda. Right? So vertex, there is a separating set which is cardinality less than or equal to the edge separating set, and that is the proof. Okay. Okay. Again, and y and z, right? So you have a two connected graph and any three vertices in it. Now you can either prove or disprove that there is a path, which contains all the vertices, right? A path in the graph which contains all the vertices x, y, and z. I'm not talking about walk, a path itself. The second is that I define something that a chord is basically an edge that connects two non-consecutive vertices. So let me give an example. Okay, so I have a cycle, let's say. and I add this edge, let's say. Okay, so this edge, it is a chord because this edge connects two non-consecutive vertices of this side. Okay? But these edges are not chords, right? Even though this path connects this big cycle, right? These edges are not chords. But this edge is a chord because this edge essentially connects two vertices which are not consecutive on this cycle, and therefore it's called a chord. So chord is basically is an edge that connects to non-consecutive vertices of some cycle of the graph. Now, so draw a two-connected graph, right, without chords, okay, and which is different from a cycle, right? Now, right? I want you to construct or do the following if possible, right? And if not possible, again give justification for that. So here are the things that first you have to construct a 10 vertex graph for which the vertex connectivity is strictly less than the edge connectivity, strictly less than the minimum degree. Then construct a two connected graph with exactly two bridges. Okay, let's construct. Then construct a three regular graph with vertex connectivity is equal to 2 and edge connectivity is equal to 3. Then construct a four regular graph with two bridges. So these are the questions for your homework. Now, so why is this connectivity important? Like for example, in a practical situation, right? You have let's say communication network, right? Now, if you have a communication network and then you have you can have communication disruptions, like if some vertices or edges are destroyed, and then there maybe at some point there is no way to contact from one node to another node, right? So if something like this happens, then the network becomes faulty, right? Like, there is no there is a failure, network failure, right? Communication failure. Now, the communication is more robust, like, or more reliable if by deleting some of this, removing or failure of some of these nodes will not cause a complete communication shutdown between any pair of bits. Okay? So basically, such failures of the nodes are technically called a fault, and then the fault tolerance or reliability of the network is basically represented by the connectivities, right? The vertex and edge connectivity. And one can ask several questions on this, but I will probably not go into that. So one of the reasons why this is important is that, like, when you are making such a fault tolerant network, and then the reliability I want to be slightly large, like we fix a number and say that even the failure of this many nodes or lines will not make the graph disconnected or still have the communication possible, right? So then we can ask, see, when I am going to build a network, right, what is the minimum number of edges that is required, right? The communication lines that is required, so that I have a good degree of fault tolerance, right? So optimization question is to find out a graph with the minimum number of edges whose reliability or the connectivity is high. Right? So this is natural to this exercise that show that if a graph is connected with n vertices, then it must have at least ceiling of kn over 2 edges. Right? graph is k connected with n vertices. It must have k times n divided by 2 ceiling, that many edges. Then fifth question is to construct, in fact, a graph that attains this bound, right? I mean, that you don't need, I mean, you can find a network design where you have this, you can achieve this reliability without using any extra edges. You can do it exactly k n by 2. Okay? So this is basically attainable and sharp. Okay. So now we define what is called local connectivity. Suppose you have, you have a graph, right? And you have two vertices which are not, which are distinct, right? So U and V are distinct vertices. Then I define the local connectivity between these vertices U and V as the minimum or as the maximum number of pairwise internally disjoint UV paths. That I have, so in some sense that makes sense, right? Like you have two vertices, right? You have several paths between them, right? And they are internally disjoint, means that it becomes more and more robustly well connected, right? So that's the connectivity between pairs of vertices. So in this example, right, you can look at what are the local connectivity between pair of vertices. Let's say between 1 and 2, right? Between 1 and 2, what is the local connectivity? So you want to look for the internally disjoint path between 1 and 2, right? So for example, this one is a path, right? Then I find another path, right? So there are these two, and I know that there cannot be more than two because there are only two edges, going out of one and to these vertices. So I cannot use them more than once, right? So therefore, I already have two. So therefore, this is actually best, and therefore this is equal to between 2 and 7, right? 2 and 7, I can go from 2 to 4 and then reach 7, right? 2 to 5 and 7, and then 2 to 6 and 7, and each of these are internally disjoint between any two of them are internally disjoint, right? Therefore pairwise internally disjoint, therefore local connectivity is actually 3. And then you can ask what between 1 and 9, right? 1 and 9 has 2, you can see, and then it's actually equal to 2. 3 and 8, again 3 and 8, 3, 6, 8, and then 3 to 5, 5 to 2, 2 to 4, and 4 to 8, right? That is another one, right? So there are two there. So yes, so this is what, right? So you can look at any pair and then look at this. What is this connectivity, right? And that tells you this number. Now, local connectivity, right? So earlier we saw that if the graph is two connected, right, between any two pair of vertices, the local connectivity is at least 2, right? That you have two internally disjoint paths between them. And one can actually generalize this, and what Menger's theorem does is to basically connect these two parameters of local connectivity and connectivity. Right? If the graph is k connected, then you are saying that you will be able to find k internally disjoint paths. The local connectivity is at least k between that, any pair of it. So what Menger's theorem does. So Menger's theorem of connectivity says that if U and V are non-adjacent vertices in a graph G, then the minimum number of vertices in a UV separating set equal to the maximum number of internally disjoint UV passing. And you are going to minimize, right, the for any pair of vertices, you are to minimize the local connectivity, then you will actually get the connectivity of something one can show. In fact, in some books they actually define the connectivity as the minimum overall pairs, the local connectivity of that pair, and that is defined as a connectivity, and then show that The Menzies theorem basically connects it to the cardinality of the vertex connection. So in either way you can prove it. They are kind of equivalent because of Menzies theorem that connects between these two notions of connectivity.